So we've got one end of a spring is attached to a solid wall while the other end just reaches the edge of a horizontal frictionless tabletop, so that is important, which is a distance h above the floor, so that height right there is h. A block of mass m is placed against the end of the spring and pushed toward the wall until the spring has been compressed a distance x. So that is the compression distance of the spring. The block is released, follows the trajectory shown, and strikes the floor a horizontal distance d from the edge of the table. So the range, so to speak, of the block is d. Air resistance is negligible. So very first question here is, it says find the time elapsed from the instant the block leaves the table to the instant the block strikes the floor. This part of it is a horizontal projectile problem, and they love to mix the two. So on a free response, you always have to show the initial equations that get you to the information. So this is the third equation that we call it on the kinematic sheet. So your displacement is equal to your initial velocity times your time plus 1/2 times your acceleration times your time squared. There is no initial y velocity for a horizontal projectile, and your acceleration becomes g, since that is the vertical part of it. Rearrange, and you get the time is equal to 2 times your delta y over your g. The very last step is you just have to make sure that you use the terms they do. So they're calling that vertical displacement h there. So the time to strike the floor is radical 2h over g. The next question says, find the horizontal component of the velocity of the block just before it strikes the floor. So we can figure this out because we know the horizontal velocity never changes. And we know, and again, you could look at this as the third equation, it's just there is no acceleration in the x direction. It's got a constant speed, so that's basically it right there. Or if you can just actually write it like this and use the definition of velocity. That's okay as well. So now we just have to plug in the bits of information we have. This range that we're talking about is this d right here. So capital D is the range, and the time is the one that we just found. So radical 2h over g. And you can leave it just like that. Your math teacher will tell you that that's not okay, but it's fine. You can leave it like that, and they'll give you full credit for it. So now they say find the work done. I want to show you the right way to do it, or the easy way to do it, and then another way to do it, which a lot of people actually try and do, which winds up being a lot harder. So the easiest way to do this is to realize that the work done on it is equal to the change in the kinetic energy. So we know what speed it leaves this table with. We just solved for that. It's horizontal speed. So that speed was given to it by the spring. So the work done by the spring is equal to the block's change in kinetic energy. And that is kinetic energy final minus initial. But it had no initial velocity, so it's just the final. And that will be 1/2 times its mass times that velocity squared. So in that regards, we almost have everything. The mass is actually written as a capital M, and the velocity from the previous one, we've got to square that. So it was d in the numerator, so that becomes d squared. And then the denominator, we had this radical, so that actually, all gets gone away. And so it's 2h over g down in the denominator. So let's clean that up. That's pretty messy there. We've got m times d squared over 2, I'm going to think of that as a fraction, multiplied by the reciprocal of the other fraction, like that. And then if we put it all together, it's m d squared times g over 4h. So a bunch of different numbers there. That's the best way to do it. Here's what a lot of people want to do. They want to say work is equal to force times distance, and they realize that this is the force of the spring. So they're like, oh, that's the force of the spring, and the distance right here is x, which is true. But here's the problem. The force of the spring is not constant. So a lot of people go to plug in Hooke's law here and say that the force of the spring is the spring constant k times the distance that you compressed it, x, and then times another x. There's two issues with this. One is we don't know k. So that really should end it right there. But another issue is this route here, that is not the force that it pushed the whole time. that is the maximum push it had when it was compressed all the way to x. So if you did know k, let's say, and you were going to use this, you would have to actually take the average of the force. And this would be the maximum, kx, but the minimum 0 when it's all the way at the end. So the average would be this over 0. You'd have to divide that by 2. But in this case, it doesn't even matter because we don't know the spring constant. But now that we know the work done, which also means the kinetic energy, we just wrote that the work done was equal to md squared times g over 4h. That work was done by, you could think of it again, and you could go this route of force times distance, but the better way to think is that came from the kinetic energy of the spring here. So now we just need to solve for k. So multiply each side by 2 and divide each side by x squared. And that 2 will cancel partial the way with that 4, so you get md squared g over 2h x squared is the spring constant.